Yeah, I recently purchased an Edis B200 software-defined radio. It's USB 3.0 up to 100 something megasamples per second, 50 megahertz to 6 gigahertz. I've made a box for it from a Hammond enclosure. But anyway, it's got a TXRX on it and another RX port. And what I've been wanting to do, since this is the first portable SDR I've had, is try to come up with an antenna for it. I've seen other people ask this question on some of the mailing lists. Are there rubber deck antennas that will cover, not DC to daylight, but let's say 50 megahertz to 6 gigahertz? No, there aren't. Most of these antennas are helical monopoles. They're cut for a certain frequency, say 2 meters, 140 megahertz, maybe 900 megahertz ISM band, all the way up to 2.4 gigahertz. But you're only going to find them in probably 10, 20 megahertz bandwidths. So what I wanted was to find a whip antenna that I could just vary the length of to tune it to the length that I need to form a quarter wave monopole. So what I found is this Nagoya NA-773 2 meter 70 centimeter amateur radio antenna. The nice thing about this, it's extendable whip. It'll extend from 4 inches all the way up to 12 inches in 6 sections, and clumps it back down so we can tune it to achieve the quarter wave monopole. It's got a female SMA on the end, kind of a low quality female SMA. The female contact is recessed in there about 1 millimeter, but that's okay. I've already taken one of these things apart, so I know what's inside and how to fix that. But since this is supposed to act like a 2 meter antenna, obviously a quarter wavelength is going to be a half a meter. So this is acting like a little bit of an electrically short monopole, not that short, but anyway, with these 2 meter antennas, they have typically have inductors inside of here because a short monopole is going to have a lot of capacitive reactance. So you need to cancel that capacitive reactance with a series inductance. So inside this thing is a inductor, loading coil as it's also called. The problem is that once we get past VHF or low UHF, it's going to act like an open circuit for anything higher, and I want to use this thing all the way up to 6 gigahertz. So what we're going to have to do is modify this thing to remove that loading coil, and we'll fix that recessed SMA in the process. So the plan is to take and mount this thing with a swept male-to-male SMA bend and stick it right on there like that. Screw it on and just be able to adjust the length of the whip to any length you want to achieve coverage from UHF, VHF to 6 gigahertz. Any of these quarter wave antennas, they require a counterpoise. Some people call it a ground plane, but it's really a counterpoise. The metal case is going to be the counterpoise, or if you don't have the case, the circuit board itself. So all these require a counterpoise to achieve a proper input impedance. And this thing, if you don't have a counterpoise, let's say on a handheld transceiver, your body is a counterpoise, but you always require a counterpoise. So what I'm going to do is I took and made up this piece of brass shim stock right here. It's about the same dimensions, about 6 inches long, 4 inches wide as the Edis B200. So I've taken and soldered the this length of SMA right here, 086 rigid cable, male to male. So I've soldered it on there. So this is simulate the B200 circuit board, the counterpoise. Then we can take and screw this antenna on here. Now the cable's hooked up to the network analyzer. So I'm going to be able to take a look at the input impedance of this thing as I move it around. And what you're going to find is that the loading coil in here starts about right there. So we do have a little bit of a short section right here before we hit the coil. So this is going to act like a very short monopole at high frequencies, let's say over a couple of gigahertz. Then we have the loading coil, and then we have the extensible whip. So we'll screw this thing on here and see what the impedance looks like. Alright, so I've attached this thing to my network analyzer. I've put the done the calibration right here at the end of the cable, so this is a reference plane. So what I'm going to do is run my finger along this antenna. We've got the lower section of the base here, which the upper section has the coil, and the lower section is just the connector. So as I move my finger along this lower section, you're going to see a response on the network analyzer. You know, the SWR is going to change all the way up to 6 gigahertz. If I run it along the base length of the cable right here, it's also going to see that because this part is radiating right here. It's part of the counterpoise. As we move down onto this ground plane right here, you're not going to get much radiation off here. It's going to act as a true ground plane. With this short section of cable, we're going to get radiation here. We get radiation off the lower section of the inside. But as we go higher in frequency past 3 gigahertz, that choke's going to kick in, and we can run our finger all along this thing and change the length. And you're not going to see much response above 3 gigahertz, again, because this thing is made to operate VHF and UHF. Right here, I'm plotting from 50 megahertz to 6 gigahertz, the VSWR and the network analyzer, starting from 1 going up to 11 at the top of the reticule. So what I'm going to do is I've got a marker right here. The marker number 1 is going to be at 145 megahertz. 3 gigahertz is right about in the middle of the band. So what I'm going to do is start running my finger at the top of this monopole. It's collapsed right now. The whip is collapsed, and you can see it's not changing much above 3 gigahertz. And as I move my finger down and get to the base of this thing where the loading coil is, now you can start to see the change. As I get my finger all the way to the bottom and now start touching the SMA connection, big change right there in the response at 3 gigahertz and above, because the base of this thing is radiating and the cable bend is radiating also. I've moved my finger along the ground plane and the cable in there, not much change at all. So the ground plane is an effective counterpoise, but right where the base is, we get radiation. So what we want to do, obviously, is remove this coil so we can change the length of this whip. So what I've done is I've stored the trace into memory with the whip collapse, and then the real-time measurement is in yellow. The trace is storage trace is in orange. So then I've extended the whips, and that's what you're seeing in real time. As you can see, at 3 gigahertz and above, they're right on top of each other. There is no difference between the whip being extended and the whip being collapsed. However, down below 3 gigahertz, especially down where marker number 1 is right here at 145 megahertz, now we're down to VSWR at about 3.5, which is, it's not great, but it'll work for a HT antenna. But above that, we're all over the place. We'd like to be able to at least tune anywhere between 2 meters and 6 gigahertz with a preferably 3-to-1 VSWR or better. So now we remove that inductor on the inside at the base of the monopole. Hopefully we're able to collapse it and adjust the VSWR up here above 3 gigahertz and try to get a match somewhere. We don't know where that length is, but we can adjust and look at signal strength to figure it out. Okay, to start the modification, what I want to do, and I've already taken one of these things apart so I know how it works inside. There's 4 grooves right here. We're going to take a Dremel tool, one of the thin cutting wheels, and slice right through the plastic right here and remove this bottom section. When we get that loose, this whole piece is going to twist and unscrew from the center pin, or the female center of this SMA. Now the female center is actually threaded, as is the Teflon, so this whole steel connector and the plastic base that it's molded into is going to unscrew, and we'll be left with just the inductor and the center pin of the connector. All right, I've got my Dremel tool here with the fine cutoff wheel, and here's the antenna, and I've also got safety glasses on. You don't want this cutting wheel to explode in your face. Take an eye out. So what I'm going to do is fire this thing up and cut through that first groove to get the center section off. All right, it's cut through. It looks real rough, but that plastic will clean right out. Now we can just take it and twist this thing, and here it's going to start unscrewing. There it goes. All right, that actually didn't work out the way it was supposed to. You know, I took the previous one apart, and what's supposed to happen is you're just supposed to be able to unscrew this, and it should pop right out. And there's the coil form insulator. And the SMA female connection is supposed to be threaded. This one is not. It's just knurled, and it slip fits into the Teflon insulator. And the loading coil, of course, was wound around the insulator right there and soldered to that base and soldered to there. That's not what happened. When I pulled this thing off, it actually unscrewed right there, and this base remained back inside there. On the original one I took apart, the insulator was not threaded. It was actually press fit into there, and actually, so I used a soldering iron to heat it up and yank it out. So I took this one apart. You look down in there, there's actually a little bit, there was some hot glue in there that was holding this in. So when I took it apart, this insulator was left in there and the coil was still in there, so I just took a pair of pliers and yanked the coil out. So I was left with the insulator. Then the insulator unscrewed from the base, and the base was left down in there. Pretty much just like that. So I had a pair of hemostats. I was able to get down in there. First I scraped out some of the hot glue, and as it'll get a hemostats along the edge and twist it and pull it out like that. Now that everything's taken apart, what I want to do is take and remove this insulator and solder the bottom section directly to the top section. And then we're going to have to cut down the base so the SMA female pin is flush with the Teflon insulator. So if you take and you line up, you look at approximately the length of that insulator. It starts from our first cut down to the top of the sticker, so we're going to want to make our remaining cut just a little bit above the top of that sticker, and if it's too long, we'll trim it down with a Dremel tool. Better to cut it a little long and be able to trim it than cut it too short. Alright, I took the razor knife and used it to scrape the surface on both of these brass ends, and these have to be very clean because we're going to solder to them, so I'm going to take and try to align it straight like that and solder it together. Alright, there's a tip. I'm going to take and use a flex pen to pre-tin this. Use plenty of flux, as the brass is sometimes kind of difficult to solder, so get it nice and wet with flux, and pre-tin this section and pre-tin the other section. Alright, that's soldered on there now. I use good old-fashioned lead solder. It gives flows a little better, has a little bit lower melting point than the normal silver solder I'll use, but clean that joint up and that's looking pretty good. It's nice and straight. You know, the two ends of the pieces are flush together. Now, obviously that's going to fit down inside of there, but this section is too short, so now I'm going to take the Dremel tool and make a cut about right there, make it a little bit long so you can trim it down. So that's going to end up flush now with the Teflon of the SMA connector. Alright, this has been cut down. I did end up cutting it down right about where the sticker is, where I thought it was going to be. So, and clean things up, blown out the dirt from inside that hole, and clean some stuff off, clean the surfaces off with alcohol so we can glue it together nicely. So that's going to fit straight down in there now and push together like that. And you can see the connectors now almost flush with the Teflon, right where we want it. And this is just going to be filled in with some epoxy to glue it together. Alright, before I epoxy this thing back together, I went ahead and mounted it back up on the dummy counterpoise that emulates the B200 card or enclosure. So now we're going to take a look at the VSWR, primarily see what happened to it above 3 gigahertz now that that loading coil is gone. And alright, again, we're going from 50 megahertz to 6 gigahertz with the VSWR going from 1 to 11. The orange trace is the previous trace that was stored before the loading coil was removed. Now the whip is collapsed right now. Now look at the difference. Now instead of having a VSWR probably up above 15, we're down to 4 to 1 here, probably around 4 gigahertz or so. And it moves up and down slightly, you can see. And down here, this was our first resonance. We take and now I'm going to take and extend this thing all the way. You can see in orange our original resonance of 2 meters is it's at a 7 to 1 VSWR now. I'll take and move marker number 1. So our first resonance with the whip fully extended is 200 megahertz approximately. Now if I start reducing the whip length, I'm taking and shortening the thinner sections because we want a wider section to give us more bandwidth. You can see that first resonance is increasing in frequency. If I take and shorten the thing all the way down, you can see now it's moved up to approximately 600 megahertz. So with that first, taking and going from a fully collapsed to fully extended whip, we can maintain 2 to 1 VSWR, a little bit under that, from 200 megahertz to almost 600 megahertz. Actually almost 700 megahertz. 3 to 1 would be 760. Now let's take and extend it all the way again. Now if you take a look at the second resonance right there, which is going to be at marker number 1, that's approximately 575 megahertz. Now we start taking reducing that whip section down again. You'll see that it's moving higher in frequency. We'll bring it about right there. It's not fully collapsed. There's about 1.5 sections out. And move the marker back. It's about 3 to 1 VSWR. Now we're at 1.2 gigahertz. So using a second resonance amongst the fully extended or fully collapsed whip, we can maintain a 3 to 1 VSWR from 600 to 1200 megahertz. And we're going to have the same thing with the third resonance response, and some resonances after that. What's interesting though is this band right here. Notice we haven't been able to pull this down between markers 1 and 2. That's approximately 1.8 gigahertz to 2.2 gigahertz. 1.8 right there, 2.2 right there. That band can't seem to pull that down below an 8 to 1 VSWR. With a B200, having a high power amp in there, so the VSWR probably isn't going to be an issue on transmit. It's going to reduce your sensitivity on receive somewhat because we still don't know what the optimum noise match for this thing is, but it should actually still work quite nicely for receive over a wide bandwidth. Now we go and look at the response above 3 gigahertz up here. Now as I take and extend this whip, you can see that I'm getting resonances as I pull this thing all the way out. And you can see if I run my hand up and down the thing now, look at that change, whereas before with the orange trace, it didn't matter whether it was fully extended or fully collapsed. It was always the same because of that loading coil in there. Now we can see the resonance move through. So depending on the what sections I have out, I can maintain a 3 to 1 VSWR all the way to 6 gigahertz. So the only poor spot again on this thing is 1.8 to 2.2. Otherwise, depending on how the whip section is arranged, you should be able to cover a 3 to 1 from 200 all the way to 600. 200 megahertz all the way to 6 gigahertz. So the problem is, how do you know how many sections you have to deploy on the thing? That you may want to measure beforehand, or actually try to rig up through a non-resonant piece length of wire on port 2 of the USERP and try to do a full half duplex, so we can receive on one, transmit on the other, and just sit there and adjust the whip length to maximize the signal. Would be a cheap way of doing it. Directional couplers, we can't get those to go from 200 to 6 gigs. 200 megahertz to 6 gigs is a pretty wide range. Not going to get that in a small package. So anyway, looks like it's going to work okay. Now I've got some 1 hour epoxy, and take and scorch some of this out and just get a little bit on there. And you get the right amount of the curing agent in there. Take and mix it up with this toothpick. And I'll get the epoxy mixed up. Just take and get a generous amount, not generous amount, but enough to so it doesn't dribble everywhere. Get along the edge of there. And get some along there. And be careful and stick it together not to get epoxy on the tip of the SMA. We'll take and run some epoxy in on the edge right there, pack it into where the crack is. And you may want to remove this sticker just so people don't think it's a 2-meter antenna anymore. And there we go. Let this cure and we're done.